Yeah, so the way this works is the slides are on Top Hat, but when I'm showing you things on the screen, for the most part, I'm not on Top Hat because I can't write on it on the Top Hat website. So I have an identical copy of slides that's in Top Hat somewhere else where I can use my Apple Pencil on it. And so what I will do is I will mostly be going through these slides whenever we come to a Top Hat question. Then I will actually switch to the Top Hat on here, and then you will answer the question. But at the end of each lecture, all those slides will be available to you on Top Hat. Yeah.
Can you post the blank ones so that we can download them in class and write on them? Yeah, if you like to write on, it's fine.
It's a little complicated to do that because I have quiz questions in there, and then I have to not let you see the answer ahead of time, and then I don't cover usually what I plan to cover. But you have the slides will be available to you after the class. You will have recordings of the lecture. Yeah, sorry, it's just too. I'm not organized enough to make that happen, to give you the set of slides before class. And you all know totally what that's like, right? So, okay. So yeah, classical mechanics is about Newton's laws, and you can here's sort of a two-dimensional graph of how you can think about the structure of all these theories. So on the x-axis here is the typical length scale that you're studying. So if you're going to very small length scale, you're studying the physics of atoms, and at very large length scales, you're studying things as big as galaxies. And on this vertical axis is the typical speeds of the elements of the system that you're studying. So if you're going at very, very small speeds, then you're in non-relativistic limit. If you're going to very, very high speeds, then your special relativity becomes important. So for example, quantum field theory is a theory that works when that describes really well physics when you are at very small distances, subatomic scales, and these elementary particles are moving at very, very high speeds. So the theory there is quantum field theory. That's the language of particle physics, for example. Special relativity works, again, when you're in the high speed limit, but you're dealing with macroscopic objects. So you're not dealing with the complication of quantum mechanics. If you're dealing with small speeds and small inside of an atom, that's the realm of quantum mechanics. If you're dealing with things that are really huge, black holes, galaxies, etc., then this region here is described whether you're at high or low speeds by general relativity and cosmology. And then we are studying here this sweet spot, classical mechanics, where we are dealing with macroscopic objects, and they are non-relativistic, so they're not going faster than the speed of light. So this is 0.1 c, c is the speed of light. So if you're dealing with things that are below 10% the speed of light, then that's non-relativistic. Yeah.
Just a question of curiosity. What kind of macroscopic object is moving close to the speed of light for like special relativity?
I mean, it depends on what frame of reference you're in. So in fact, if you look at very distant galaxies, they're receding away from us. And if you actually measure their speed, it comes out to go faster than the speed of light, but that's a complication because the universe itself is expanding and all that kind of stuff. So that's a situation where you have a very macroscopic thing going at the speed of light. And you can imagine that at some point when we become civilization 5.0 or something, if we don't blow ourselves up before then, we might be able to build rockets that go really, really fast. Or for example, the light sail, have you guys heard about this?
Yes.
Right, the giant solar panel, and it gets pushed by photons coming from the sun. So initially it'll go really, really slow, but because it's really light and the photons keep pushing on it, so the acceleration is really, really tiny, but it's forever. So as long as the sun keeps sending out light at it, it'll keep picking up speed, Eventually, it'll go very, very close to the speed of light. We'll have to wait a really long time for that to happen. But in fact, that is considered to be one of the ways in which we might do space travel in the future so that we can approach the speed of light And the universe is still hopelessly big. I'll talk about that later. Even if you go near the speed of light, you're barely going to explore the universe. All right. Okay, so that's the end of the spiel. Now we come to proper chapter 1. And so this chapter 1 is, in some sense, a little bit boring, but it's good to kind of set up our notation here. We're going to talk about things like units and dimensions. So all these things you may have seen in some capacity before, but we'll kind of be a bit organized about it so that we're all on the same page. So here's chapter 1. So there are some, let's talk about what are called fundamental quantities in mechanics. There's 3 fundamental quantities in mechanics that are length, mass, and time. And why do I call them fundamental quantities? Is because all other observable things, like for example, the speed of a car or the velocity, the acceleration, the force, the energy, if you were to try to measure these things, you are always measuring some combination of length, masses, and times. So for example, if you were to measure the average speed of a car, you observe this car traveling, you want to measure its speed. What are you going to do? You're going to first measure the distance it has traveled, and then you divide it by the amount of time of travel. So this is a length measurement. This is a time measurement. So again, you're using 2 of the 3 fundamental quantities, length, mass, and time. So here you did length over time and you got the speed. So in some sense, the speed of the car is a quote unquote derived quantity coming from measurements of length and time. Any questions on that? So similarly, all other physical quantities in mechanics can be expressed in terms of length, mass, and time. Another way of saying this is that the units of things like speed, force, energy, etc., will always be in terms, some combination of units of length, mass, and time. So meters, seconds, kilograms, for example. So that brings us to units. So in order to communicate the numerical values of physical quantities like speed and stuff like that, we have to develop a system of units. If you say that the car is moving at a speed of 50, that could mean anything, depending on what units you put next to it. And I don't know if you guys heard, about a decade ago or something, there was a failed mission. Some satellite somewhere crashed or something because people in Europe and the US were using the wrong units and they messed up. So it was, yeah, you guys were probably kids back then, so never mind. Old reference, Google it. So again? Yeah. Yeah, that's right. It was in Mars. And it's because the Europeans were using the metric system and we were using the American system. Anyway, actually in this class, we will mostly use the metric system. Yeah, miles per hour. So here's the same thing of speed, right? So it's the same physical quantity speed. It is made up of the same physical fundamental quantities, length over time, but you can express it in many different units: miles per hour, kilometers per hour, meters per second, feet per second, and so on. And you can convert between units. 55 miles per hour is the same as 89 kilometers per hour, which is the same as 25 meters per second, which is the same as 81 feet per second. So we now come to what is known as the SI system of units, which I guess stands for, in French, System International, or Système International. I don't know how you pronounce it. Anybody here speak French? No, go. So in SI units, we will always specify length in meters, mass in kilograms, and time in seconds. So therefore, your speed will be in meters per second. Your mass will always be in kilograms as opposed to grams, and so on. So whenever we work in these sets of units, we say that we are working in SI units. Yeah, you can use minutes, but then you're not in SI units, so you will convert from seconds to minutes. And in fact, we'll talk a lot about converting between different systems of units. Yeah, so in some cases, minutes, is it a dog that you're looking at? Is it a corgi? Okay.
It's like a little black fluff.
I think it's the one in the office across the hall.
Oh, okay.
She was out there doing tricks before class.
Someone across the hall, like in an office or in a class?
And always
office.
Professor Bunton's dog.
Oh, Professor Bunton's dog. Okay. All right. Okay. Yeah, I don't know what the rules are. Can you bring dogs to class or?
I think if they're like service or
Okay.
service dogs that are
Yeah.
emotionally supported.
If you need emotional support, feel free to bring a dog. So, yeah, any questions on this so far? Okay, so now when I say that in the SI system of units, length is measured in meters, mass is in kilograms, and time is in seconds. So in this situation, our next problem is how do we define each of these things? What do we mean by a meter? What do we mean by a kilogram? And what do we mean by a second? So this is like real boring. There was literally in 1960, there was a committee somewhere in Paris, and they made decisions about what to call a meter, and what to call a kilogram, and what to call a second. And the simplest one is, what is 1 kilogram? It is literally the mass of something that sits in a museum somewhere in France. So whatever that thing, whatever mass that thing has, we call that 1 kilogram. And it's all protected and yeah, go ahead.
So if we're doing an assignment and we're dealing with grams, like kilograms, do you want us to convert that to kilograms?
Wait, say it again.
If we're dealing with say like 100 grams, do you want us to convert that to what is that? 100 kilograms?
No, as long as you're working in a consistent system of units, that's fine. You can work in whatever system of units you want. SI system of units is very commonly used, especially in Newtonian mechanics. If you're dealing with things inside of an atom, for example, an atom is like an angstrom, that's 10 to the minus 10 meters. You don't want to keep writing 10 to the minus 10, so you may use different systems of units. So yeah, in some problems, like on WebAssign or whatever, and in fact, my apologies for that, but they will give you things in weird units so that you have to convert, make them all in the same system or whatever. So they might give you something in grams and something in meters. So you could, in principle, compute something that has units grams times meters times whatever. That's fine too. But then usually they will tell you in the answer box that you have to answer it in certain units. So you have to then convert it from the information they give you to whatever units they're asking the answer in. That's just sort of a life hack. Often if you're getting the wrong answer, check that you are entering the number in the units that they are asking. Any questions on that? Okay. And then the idea here is that, then how do we know if something else is a kilogram? Well, you compare it to this thing right here. You put them both on a weigh scale, and if they balance, then that other thing also is 1 kilogram. And how do you know if something is 2 kilograms? Well, now you have this object that you know is 1 kilogram, and you have this thing sitting in Paris that's 1 kilogram. You can put them together on a thing, and then balance with something else, and if they balance, and that other thing is 2 kilograms, and so on. So in this way, you can, and then they send out the specifications to the factories or whatever to make 1 kilogram things or 25-pound dumbbells or whatever, which you will convert from kilograms to the American units, and so on. Meters, again, how do we define 1 meter? You could imagine that, it's just the length of something that sits somewhere in a museum. But we have a more sophisticated way of doing that because things contract and stretch and whatever, depending on the temperature. So people want a more reliable thing. And so It is currently defined in terms of the distance traveled by light in a vacuum during a given time, blah, blah, blah. These are just more and more sophisticated ways of doing it. But the important thing for us is that it's a well-defined thing, and that is how we built this. Is this a meter? I don't know. A meter stick and things like that. Similarly, seconds, you can again maybe make a second as the time of something that is very periodic and very reliable. And then you can say so many oscillations of that thing is 1 second or whatever. And again, they use a very fancy way of doing it. They define it in terms of the oscillation of radiation from a cesium atom. So very, very precisely. So a bunch of quantum mechanics going on here. But in the end, this is the most sophisticated way of doing it. I'm sure in the old days when cavemen were around, it was like the amount of time it takes Bob to take 1 step or something. And that was a second. So we got more and more sophisticated. And now we're looking at oscillations of radiation from a cesium atom. Okay. Here are some cool numbers you can memorize and impress people at parties. So here's different types of things that have different lengths. Going from a very small length, the diameter of a proton is about 10 to the minus 15 meters, really, really tiny. That is, you take a meter and you break it up into 10 to the 15 chunks, and each one of those chunks is the size of a proton. And what is 10 to the 15? That's 1,000 trillion. So you take this meter stick and you break it up into 1,000 trillion bits. Then each one of them is going to be the size of a proton. Or another way of saying that is that there are basically 1,000 trillion protons. If you line them up, they will be 1 meter. The distance from Earth to the nearest star, a star called Proxima Centauri, is 4 times 10 to the 16 meters. What is that? That's about 40,000 trillion meters. And I think if you do the math, it comes out to be about 25 trillion miles, something like that. And talking about the light sails and all that kind of stuff, another way of saying this is that this is about 4.2 light years away from us, meaning that it takes, if you turn on a flashlight, it will take 4.2 years to reach Proxima Centauri, which is the next nearest star to us after the sun. But the sun is about 8.5 light minutes away. So if you turn on a flashlight, it will take about 8 minutes to reach the sun. It'll take about 4.2 years to reach the next nearest star to us. So even when we do the light sail thing, if we are able to wait long enough and it gets to an acceleration or a speed close to the speed of light, it will still take you 4 years just to get to the next nearest star, which is one of 200 billion in our own little galaxy, which is one of trillions of galaxies in the universe. So it's pretty hopeless. So if you're stressed out about exams, things, sometimes, just realize that none of this matters and it takes the stress off, right? Yeah, go ahead.
What's the estimated time it would take for the light sail to get to light speed?
I don't know. You can do a calculation where you can Google what is the acceleration of the light sail. Maybe we'll make that a problem. First off, the Newtonian mechanics will break down, so we can't use, because as you start approaching the speed of light, you have to then switch to special relativity. But we can still do the wrong calculation in Newtonian physics and just see what the estimate is. So if you Google what is the acceleration, in chapter 1 or 2 later on, we can figure out how long it takes. That'll be like a physics 1 problem. So remind me of that if I forget, and we can actually try and figure that out. Okay. Any questions on that? Here's some range of masses. An electron is about 10 to the minus 30 kilograms. And by the way, you guys know about scientific this exponential notation, right? So when I say something is, let's look at this. The mass of the sun is 2 times 10 to the 30 kilograms. So when I say 2 times 10 to the 30 kilograms, what that means is that this is 2 times 1 followed by 30 zeros. Right, that's what that means. What about this 9 to the minus 31? So if I go 9 times 10 to the minus 31 kilograms, that is the same as 9 divided by 10 to the 31 kilograms. So something to the negative power is the same as 1 over that thing to the positive power. And so what this is this is 9 divided by 1 followed by 31 zeros kilograms. So it's a really, really tiny number. Any questions on that? Since there's some biology people in here, bacterium, 10 to the minus 15 kilograms, mosquito, 10 to the minus 5, frog, 10 to the minus 1, and so on. You can use this in your biology class. So professor, if a bacterium weighs about 10 to the minus 15 kilograms, how is this possible? Something like that. I don't know. Okay. Tough crowd. All right. So time intervals. The time required for light to travel across a proton. So you turn on a flashlight. How long does it take to travel? What is it? How many trillions of bits was the meter stick? Anyway, a proton is really, really tiny. And if you turn on a flashlight at one end of it, how long does it take the light beam to go across it? Ridiculously small time, 10 to the minus 24 seconds. That's about 10 to the minus 24 seconds is 1 trillionth of a second. That's how quickly it can go across. It will still take 4 years to get to Proxima Centauri, but it can go across a proton really fast. Any questions on anything? Any questions from people in Zoom? Feel free to unmute yourself or type comments in the chat. Okay. Let's see. Units. Okay. So this was the SI system of units that we talked about. Length is in meters, mass is in kilograms, time is in seconds. And once you have this, then you can build any other crazy system of units you want, because that'll be in relation to the SI system of units. So for example, in the CGS system, you measure length in centimeters, and you define a centimeter to be 1/100th of a meter. Or you measure it a mass in grams, and you define a gram to be 1,000th the mass of 1 kilogram. So it's 1,000th the mass of that thing sitting in France in a museum somewhere. And seconds is still seconds. There's the US customary system, which almost nobody uses. Length is in feet, we do use that. But apparently mass is in slugs. And I don't even remember, it's some number of kilograms, some fraction, or I can't even remember if it's bigger or smaller than a kilogram. It's something. And then there's seconds. Oh, I actually give the conversions here. So there are 100 centimeters in 1 meter. There are 1,000 grams in 1 kilogram. There are 3.281 feet in 1 meter. And then there are 0.0685 slugs in a kilogram. Okay. Any questions on that? So is a slug bigger or smaller than a kilogram? Is one slug bigger or smaller than 1 kilogram? Say it again?
I think a slug's bigger. One slug.
Yeah.
Somebody give me your reasoning if you believe in what you're saying.
If 1 kilogram is even 1 slug, then that means it's gonna be multiple kilograms to be 1 slug.
That's good. That's a good logic, right? If 1 kilogram is just 0.685 slugs, then one slug will be many kilograms. So yeah, that's right. So a slug is bigger. I think that's the last time we'll ever talk about a slug. So unless WebAssign is trying to mess with you. Any questions on that? Actually, somebody should Google how they came up with the definition of slugs. There's probably some history behind it. Is it actually the mass of a slug or something? Who knows? Let's do a example of converting units. Let's say a car is traveling at 55 miles an hour. What is the speed of that car in kilometers per hour? And all of you may have taken some previous class before, maybe chemistry or something, and you probably have your own way of converting units. But again, I will just go through it here carefully. So what we want to do is we want to go from miles per hour to kilometers per hour. And so we have to basically convert a mile into kilometers. The hours are still the same. And then we look up on the internet that 1 kilometer is about 0.621 miles. So therefore a mile is bigger than a kilometer. And therefore 1 kilometer divided by 0.621 miles is 1, right? They're the same thing. So the trick I will use to convert units is that I will take my 55 miles per hour and I will multiply it by 1. That doesn't change anything. I can always multiply by 1. But then I will take this 1 and I will write it as 1 kilometer divided by 0.621 miles. Because they're equal, this ratio is just 1. And then you see what happens. The miles here cancels with the miles here, and then you're left with just kilometers per hour. So the miles cancel, you're left with kilometers per hour, and then you have 55 divided by 0.6281, 0.621, and therefore you do this math here, 55 miles per hour is the same as 89 kilometers per hour. Questions on that? Now keep in mind that I could have also taken this equation here, and I could have instead said 0.621 miles divided by 1 kilometer. That is also equal to 1. So when I'm multiplying it by 1, I knew to take this way of writing 1 rather than this way of writing 1 because I wanted the miles to be in the denominator so that it can cancel this miles, and I wanted the kilometers to be in the numerator so that I can get to kilometers. So you usually have two options of writing the 1. You just look at the one that makes sense for you to get from one system of units to the other. Any questions on that? Here is, I think this is a top hat question. See if you can figure out what is the area. So the area of some floor or something is 35 meters squared. The question is, what is the area in centimeters squared? So can you convert a meter squared to centimeters squared? And I think this is a top hat question. And my hint here is that a meter squared, you should think of that as a meter times a meter. And you're trying to convert each meter factor to centimeters. And keep in mind that 1 meter is equal to 100 centimeters. So see if you can figure that out, and I will switch to top hat here. And you can feel free to chat with your neighbor if you want. So this thing is frozen. I don't know why it seems to be. Oh my God, what is happening? Continue presentation. Okay, there it is. So I keep going forward, keep going forward. Oh my God, what does it keep? Okay, fine, exit full screen. Let's see here. Okay, so here's the question. Here is the top hat form of it. So again, you will just enter a number, and that number will be units of centimeters squared. And so let's see what we get. Just the number. But the number should be in units of centimeters squared, but just enter a number. "25 seconds. Oh, does anyone need more time? Let me open it again. I'll give you guys another 20 seconds. And by the way, just so you guys know, were you guys able to see the lectures from last time on Top Hat? You have to click on the, I think it says assigned or something. It's like under the assignment thing where I assign it to you like as a reading. So that's where the lectures are, in case you couldn't find it. Okay, 10 seconds. Okay, it's kind of all over the place. Let us see what the correct answer is. It is 35,000. So it was a matter of, wait, is that right? Let's work it out. Oh, I think maybe I marked the answer wrong. Sorry. So here, yeah, so let's work out the correct answer. So we have here 35 meters squared. That's the same as 35 meters squared, and I want to multiply it by 1. Well, I know that there's 100 centimeters. Actually, let me switch to this here. Let's go here. So I could write this as times 1 times 1, which is equal to 35 meters squared times 100 centimeters in 1 meter times 100 centimeters in 1 meter. So now you see that there is a meter squared here, and then this meters times this meter is also a meter squared, and then this centimeters times the centimeter is centimeter squared. These two things together is this 100 centimeter over 1, the whole thing squared. And so this, in the end, becomes 35 times 100 squared. That's basically 10,000, 10 to the 4. And then you will end up with centimeter squared. And so that is 35, 1, 2, 3, 4 centimeters squared. So did I mark the wrong answer there? Let's see. Oh, I did. Okay, so sorry, my apologies. The ones who said 35 with 4 zeros is correct. But I think this is all participation, so you should get full credit. Any questions on that?
This is the most thinking of 10,000s.
Say it again.
I guess I have my mind set to millimeters instead of centimeters.
Oh, millimeters is, yeah, that's right, yeah.
I guess I was so used to doing that. I didn't.
That's right.
Plus billions were squared, we didn't have to worry about squared.
Say it again.
Plus billions were already squared.
Sorry, I can't hear you.
I don't think we have to worry about squares since you could really have something that's already squared.
Well, what you're doing is you're converting meter squared. So a meter is a meter times a meter. So you're taking each meter factor and you're converting it to centimeters. So each time you do that, you're getting one factor here. And then for the other meter, you're getting another factor here. So that's why, so if you have meter cubed, if it's like a volume, then you would do it 3 times. For each factor of m, you want to convert it to centimeters. Yeah. But
You said it was a participation based, but I didn't answer because I didn't finish. Is that going to reflect the grade?
Yes, but let me just open it real quick. Yeah, if you're stuck on something after a while, if the clock is running, put something in. Sometimes I might give you credit for correctness, which might be like 10% of it, but 90% will probably still be participation. So try not to leave it blank.
So just answer something.
Yeah, I mean, do your best to think about it, and then if you can't, then then answer something. All right, I think maybe this is a good point to stop. So I will see you guys on Friday.